Hello everybody. So in this example here, I will do something before the example that I mentioned last time. So last time we discussed the example of the reactor and separator, and then there was no recycle, and then I said we are going to discuss the case of the reactor and separator with the recycle. But before this, there is one thing that is very relevant that I already mentioned before in the chapter 4 discussion, which was the last example that we used the relocation of bases strategy to do the solution. So I will revisit this quickly and I will make it clear now why we were not able to assume any information. So there is a reaction that takes place here, which is carbon monoxide plus hydrogen produces methanol plus water, and we know the fractional conversion of hydrogen inside the reactor is 60%. So again, for the degrees of freedom for the mixer, we have 3 in stream 1, 3 in stream 2, and 3 in stream 5. So we have 9 variables. We have 1, 2, 3 given variables. We have 3 equations, and we have no additional relations. So the degrees of freedom is 3. For the reactor, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. It's 8 plus 1, so it's 9 variables. The given variables are 2. We have 5 equations and 1 relation, which is the fractional conversion. So this makes the degrees of freedom is 1. For the separator, we have 5 plus 3 plus 2. We have 10 variables. We have 1 given variable, which is the flow rate of methanol in the product stream. We have 5 equations. We have no additional relation, so it has 4 degrees of freedom. For the splitter, we have 3 plus 3 plus 3, so it's 9 variables. We have no given variables. We have 3 equations and the splitter restriction, which is 2. So this makes the degrees of freedom 4. For the overall, we have 1, 2, 3, 4, 5, 6, 7, 8 variables plus 1, which is the extent of reaction. We have 1, 2 given variables. We have 5 equations. We have no additional relation, so the degrees of freedom is 2. So from what we see here, there is no unit that has 0 degrees of freedom, and we cannot assume or this is not because we don't have a basis, because we already have a flow rate here. So in the previous examples, we said, okay, it's clear that we need to assume something because we have no given flow rate. In this case, we already have a given flow rate, but no unit has 0 degrees of freedom. So whether we are able to assume flow rate or assume another information or not depends on the process, this column. And now it's going to be clear. When we solved it before, I just said I know that I cannot assume any other information, and I didn't mention why, but the reason is going to be clear now. So for the process, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's 6 plus 5, it's 11. 3 plus 2 is 5, so it's 16, plus 6, it's 22, plus 1, which is the extent of reaction. So we have 22 or 23 variables. For the given variables, we have 1, 2, 3, 4 given variables. The number of equations that we have is the summation of these, which is 10 plus 6 is 16. And we have the additional relations, it's 1 plus 2, which is this additional relation plus the splitter restriction. So this makes the degrees of freedom, the number of additional relations is 3. Now things will get interesting. So now if you count 23 minus these, it's going to be 0. And now comes the importance of this column. You can see now that the process is solvable with the given information, although we have no unit that has 0 degrees of freedom, which is a very common case in case of or when we have recycled streams. This is a very, very common case, and the reason is we have enough information, but this information are scattered. So you have some information here for the reactor, you have some in the mixer, you have some in the separator. So you don't have the information are all available in the same place for the same unit. So you have enough information to solve the whole process, but you cannot use the information to solve any of the units with the current givens, because none of them has 0 degrees of freedom. And that's why we didn't assume anything, because the process degrees of freedom is 0. So if let's say I assumed another information here, it will contradict with any other information that you have, whether it will contradict with this composition, or will contradict with this flow rate, or you might have a negative flow rate for one of the components. Anything would be expected, because you are assuming a value that you can calculate. So it's going to make some contradictions. So this is a very common case, and we already solved this problem by just playing a simple trick, which is the relocation of bases. And what we did is we assumed that this number is not given, and we put because we looked at the numbers and we found that this is 1. So if you give the reactor one more information, everything will be done. As we saw before, you can put this information here, which is the flow rate of stream number 2, and we put it as 100, and then you can solve the reactor. The reactor will lead to the calculation of compositions and flow rates of stream number 3. Now we can calculate or solve the separator, and then we get stream 7 and 4 flow rates and compositions, and from this we can solve the splitter and mixer, and we can finish everything. So this is something that we saw. So we already saw before that we can have a case. And of course, at the end we did scaling up, but we saw a case where you have units for the whole process. None of them has 0 degrees of freedom, yet the process is solvable. And before we were not able to decide whether it's solvable or not, but now we saw how you can tell this. So this is a very important thing. Without this column, you can mess up everything. And you imagine you assumed a flow rate of stream 2, and then you did the calculations, and one of the units didn't converge. You find that the in is not equal to the out. So you are wasting a lot of time without any point. You're just doing calculations that are not or don't make any sense. So we were lucky in this case, because the issue was only with 1 degrees of freedom. So in this unit we had 1 missing information, so we were able to relocate the bases from stream 7 to stream 2. This made the reactor degrees of freedom is 0, and the whole process was solvable accordingly. So this is one trick that we can use, and you're not able to use this trick or know that you can use this trick without the process column. Otherwise, what you do is you would assume flow rate at the reactor, and then you will try see how well things will go. So this is an important thing. This is a very important thing. Let's see another case. So now we saw one case where there are some other strategies than just the straightforward solution. So one of the strategies is the relocation of bases. Relocation of bases is a very useful strategy. But it doesn't work for all the cases. So let's see another case, which is the previous case that we discussed before for the reactor, and where ethyl benzene is produced, and we have a recycle stream for the whole stream. Still, we have the same information. This is the same reaction that happens. We have the same conversion of ethylene. Of ethylene in the reactor. We have the 4 relations for the separator, the relation between stream 3 and 4 in the separator. Of course, the stream numbers are different, but it's the same input and output streams. So now let's do the degrees of freedom analysis. So for the degrees of freedom analysis for the mixer, we have 3 plus 4 plus 4, so it's 11 variables. We have 3 given variables, we have 4 equations, we have no additional relations, so this is 4. For the reactor, we have 4 plus 4, it's 8 plus 1 this should be 1. I think there's something wrong here. So this should be 1. It's 8 plus 1. We have only one reaction here. We have 0 given variables, we have 4 equations, we have 1 additional relation, so this makes the degrees of freedom is 4. If it's 8 plus 1, this is 1, so it's 9 minus 5, it's 4. For the separator, so I'm sorry for this mistake. For the separator, we have 4 plus 4 plus 4, so it's 12. The number of given variables is 0. The number of equations is 4. The number of relations are 4, so degrees of freedom is 4. For the overall loop, we have 3 plus 4, it is 7 plus 1 extent of reaction, so it's 8. We have 3 given variables. We have
4 equations and no additional relations, so degrees of freedom of the overall loop is 1. So we have no unit that has degrees of freedom, and we cannot use the trick of relocation of bases because the basis is already in the overall loop. So this is not going to work here. Okay, so if you put any extra flow rate, then it's going to be an assumption of another information. Now let's look at the process. So for the process we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19 plus 1. So this is 20. The number of given variables is 3. The number of equations is 4 times 3, which is 12. And the number of additional relations is 5. If you count this, it's 20 minus 20, it's 0. So this is a very interesting case. We have no unit that has 0 degrees of freedom. The given information are already, or the given flow rates are already in the loop that has the minimum degrees of freedom. So the relocation of bases strategy is not going to work here. And we have 0 process degrees of freedom. So we have to deal with the given information without assuming anything else. So this is a very, very, very interesting case. And now we will be stuck. So in the slides that I showed in chapter 4, I just showed you the final answer, and without showing how I reached this solution. And now I want to discuss in some details what are the strategies that we follow to find these solutions, or how we can get the missing variables here. So there are a couple of strategies that I will cover here, and these 2 strategies are very, very famous strategies. And these strategies, by the way, are used by the simulation software. So if you use a process simulation software like Aspen Plus or Aspen HYSYS, it would be operating using one of 2 strategies. One of them is called sequential method, or the equation-based method. And this is what I'm going to use here. So of course it does it in a more advanced way, using more sophisticated equations, and it combines the mass and energy balance together and equilibrium relations. But in the theory, from the basic way of solving the equations, this is what we have. So the 2 methods are, or there are 2 strategies that we are going to follow. One of them is solving all the equations simultaneously, and this is what we call the equation-based. And one of them is the tiering strategy. So what I'm going to do in the coming 2 videos is that I will solve the last example. I'll solve it twice. Once with the solving the equation simultaneously, or the method of solving the equation simultaneously, and once by using the tiering strategies. So this is going to be a very interesting thing to learn. But the main point that I want to make here, and I hope it's clear now, that this column is extremely important. That this will make you able to decide what strategy are you going to follow, and whether you are able to assume any value or not, because this depends primarily on the value of the degrees of freedom that you calculate in this column. So again, you can assume that this system is missing one information, and then you will assume a flow rate in the overall loop, and after a long time you would solve the whole process, you will find out that the numbers are not matching. So this is very important. So when you have this process column, you are making a very, very simple calculation, and it is telling you a lot of things regarding the information that you have and the way you are going to follow to solve this equation. For example, you can tell from the previous example that the relocation of bases is a proper method, but now we can also, with the same calculations that we did, that tiering is not working, so we have to find something else. So next time we'll start with the first method, which is the simultaneous solution of the equations. So I'll see you then, inshallah. Goodbye.